Our next speaker is Blanca Lopez. Blanca Lopez, she's our master student here in our research center, and she works in digital electronics in the field of embedded systems and reconfigurable and evolvable hardware implemented on FPGAs. So, Blanca, when you're ready, please.
Okay, good morning, and thank you for attending my presentation. The work that I'm going to talk about is the implementation of a power-aware, multi-objective, evolvable hardware system on an FPGA. Okay, it doesn't work, sorry. Yes, but I use my own device, okay. Yes, okay, perfect. Okay, sorry. Okay, again. I will begin with an introduction of the project. The work was developed in the context of the DREAMS project and is based on an evolvable hardware system that is implemented on an FPGA and applied to the filtering of a grayscale noisy image. The design of the filter does not rely on a model or equations, but it is made according to an evolutionary approach. Each feature of the filter is identified as a gene, being the global configuration the genotype or chromosome. With that configuration, the image is filtered, and the quality of filtering is evaluated with a fitness function, here the mean absolute error. And finally, from these fitness results, evolution is performed, keeping the best configurations and subjecting them to little changes in order to evolve. The framework of this work includes evolutionary algorithms that imitate the natural selection of a species and pursue to solve problems based on randomness and adaptation to the environment. In order to evolve through generations, there are two mechanisms: crossover, where random segments of two parents are merged to form a child, and mutation, where the child is generated, mutating certain genes of a single parent. The evolution of the filter implies modifying processing elements at runtime. Modular and online modification of hardware is possible thanks to dynamic and partial reconfiguration, DPR, which allows to access the configuration memory of the FPGA through the internal configuration port, the ICAP, and load a configuration in a certain region of the FPGA, managing configuration files called partial bit streams. The evolution may not have a single objective, but a set of them. In this work, power consumption is taken into consideration, together with fitness. So the evolution turns multi-objective and is based on Pareto optimality. Finally, as the optimization of power consumption is taken into consideration, and despite the fact that most evolvable systems are usually implemented on more powerful platforms, it makes more sense to use a low-power platform. So it becomes necessary to port the preceding evolvable system, which only evolved taking into account one objective, and that was shown yesterday in the demo, in the poster session. It becomes necessary to port this system to a low-power Spartan 6 FPGA included in a wireless sensor network node called Hierarchy. Looking at the state of the art related to this work, some authors have also focused on the need of exploring low-consumption devices. In Spartan 6, the features of the internal configuration port and the morphology of the bit stream have been addressed, and DPR has been applied to several purposes, like a startup method to configure the FPGA in 2 stages, image processing, signal processing, etc. Multi-objective optimization on hardware has also been found in some works. For example, the evolutionary multi-objective design of combinational logic circuits, and in particular, Pareto optimality has been found in, for example, the evolutionary design of digital filters and power distribution systems. And the optimization of power consumption using evolutionary algorithms has been found in some consulted works. However, none of them performs a real measure of consumption in real time. Instead, they use estimation models or offline obtained values. The applications include the design of circuits, FFT processors, or the order of execution in a microcontroller. The main contributions of this work are implementing an evolvable system on a low-power platform and achieving the capability of multi-objective evolution by enabling power awareness, by enabling a real measure of consumption in real time. The milestones of this final goal are developing a hardware able to monitor the consumption in real time, build the multi-objective evolutionary algorithm, and port the preceding evolvable system to the new low-power platform. I continue with the background of this work. As I have already said, this system, the starting point of this system is the previous evolvable system implemented on a Virtex 5 FPGA and intended to optimize a single objective. This system is based on a systolic array of processing elements, and in order for these elements to be interchangeable, they are provided with a common interface consisting of bus macros. The architecture of the system is divided into a dynamic area, where the systolic array is placed, and a static area, where, besides other blocks, the array controller, which is a custom peripheral, is located. The input noisy image is read, a 9-pixel window goes across it, and there are some multiplexers that select which input, which pixel, enters the array in every cycle, and which output is taken. Once the image is filtered, the fitness is computed, and the results are sent to the microprocessor. So finally, the configuration of the array, which is the genotype or the chromosome, consists of the processing elements and the selected inputs and output. I address now the part of the implementation, starting with the creation of the reconfigurable structure in Spartan 6. It is very important to know the low-level architecture of the FPGA in order to design modules that are interchangeable and to determine the correspondence between the FPGA fabric and the structure of the bit stream. This FPGA is divided into 12 clock regions, each of them comprised of 77 columns of different types, mostly of CLBs, which are the logic blocks that are subject to reconfiguration. A regular area in the FPGA had to be found to allocate the systolic array. However, it's not completely regular at the end sites, and this means that the bit stream of the element is different depending on where the element is located in the array. And finally, the configuration of the elements has to be translated to information, so that the hardware that accesses the internal configuration port can extract the configuration from the FPGA and load that information in the flash memory. The configuration information is contained in the partial bit stream, which consists of a set of frames describing every column. Each frame consists of 65 words of 16 bits. The processing elements were designed with Xilinx ISE. For each element, 3 designs have to be made depending on the position in the array. The position and routing of the elements is supervised with FPGA editor. And finally, for each element, a system is created so that the configuration of the element is read and stored in the flash memory. The architecture of the system, which has been already partially described, comprises several IP cores and the custom peripheral, and is designed with Xilinx Platform Studio. In order to incorporate the power consumption as a parameter during evolution, some other modules have to be implemented in this custom peripheral, and this will be addressed in detail later in the presentation. One of the most relevant aspects of the implementation is the strategic layout of the system within the FPGA, and this is done with the programs ISE and Plan Ahead, and takes into account the connectivity needs and the boundaries imposed by the reconfigurable area. Finally, FPGA editor allows to supervise the design, which has to fulfill certain conditions to be reconfigurable. And finally, the system turns out as shown there, where the empty area corresponds to the systolic array. Let's see now how the system has been designed to be power aware. There are some estimation models for power consumption that estimate it, relating it to underlying physical phenomena or to the utilized resources in the FPGA. However, an evolutionary approach to a problem disregards any model. As well, a model has to be adapted to its platform, whereas intrinsic evolution allows to measure the consumption of the own device, regardless of which one it is. The first step to approach the power consumption consisted in obtaining the consumption profile of the FPGA during the evolutionary process with an oscilloscope, and consumption peaks were observed during both reconfiguration and filtering. The consumption that is optimized is the one corresponding to the filtering stage. Let's see how power awareness has been implemented. The ADC included in the node has most of its inputs connected to the power islands in which the node is divided. To measure the power consumption, the current demanded by the FPGA core is led to a shunt resistor so that the voltage drop, which is proportional to the power, is amplified and carried to the ADC. The communication with the ADC is based on SPI protocol. Xilinx provides an IP core to develop this SPI interface. However, obtaining the measurements via software was discarded because it's necessary to parallelize the measurements with the operation of the system and delimit very precisely the measurement time synchronized with other hardware modules. So the interface was implemented on hardware in the form of additional modules in the custom peripheral. These modules include a controller of the ADC to produce the SPI signals, a processing block which performs several calculations upon the consumption values, such as low-pass filtering and averaging, and finally a control module to command to perform a certain number of measurements. The power measurements are differential, which means the difference between the static consumption and the consumption during filtering. And a moving average filter is applied in order to remove the effect of noise. Finally, the development of the multi-objective evolutionary algorithm is explained. There are two possible approaches to a multi-objective problem. Firstly, considering it as an extension of the single-objective problem, defining a compound fitness function using weights. And secondly, Pareto optimality, according to which a solution is optimal or non-dominated if no other solution leads it in one objective without being worse in the others. The first option was discarded because it's not very robust, and the algorithm that was chosen to perform the evolution is the NSGA2, which introduces an operator to compare the solutions based on the non-dominated sorting of the solutions and their diversity, which is calculated with the distances among solutions. So in the event of two solutions belonging to the same Pareto front, the algorithm selects the one that is more distant from the other solutions. Initially, a random population of 4 parents is generated. For each of them, the systolic array is updated with that configuration, the static consumption is measured, the filtering process is triggered, and finally the values of fitness and power consumption are obtained. In this population, the Pareto fronts are obtained and the distances are calculated. Afterwards, the offspring are generated by binary tournament and mutation, and then the global population is formed, gathering parents and children. In this population, again, Pareto fronts and distances are calculated, and finally the future parent population is selected in order of Pareto front, and in case of draw, taking into account diversity. Let's see now how the experimental results are. At the first stage, the evolutionary process was launched, applied to the filtering of an image with a noise level of 5% and employing a mutation rate of 3, which means introducing 3 changes in the mutation of a chromosome. The final population of the evolutionary process is represented by 4 points in a graph whose axes are power consumption and fitness. It can be seen how the set of solutions resembles a typical Pareto front. 2 thresholds are also represented: the median filter, which is a usual reference to assess the quality of filtering, and the copy filter, which only passes the input to the output. So the solutions that are obtained beyond this threshold are rejected because they do not perform any filtering function. In this single execution, 2 feasible solutions were obtained, with a significant difference both in fitness and in power consumption. So in a very low power application, the filter of best fitness could be discarded. This difference in power consumption was checked designing a non-evolvable system configured with a filter operating in normal mode, and the battery level was monitored. The results show how the battery voltage drops more quickly in the case of the configuration of best fitness. It was also tested if these results could be predicted from the physical implementation of the filters, and for that purpose, each of the filters obtained in the Pareto front was simulated with X-Power Analyzer, and it can be seen how the estimated points draw again the shape of the Pareto front. I finished relating to the conclusions and the future work. As for the evaluation of the developed work, we have succeeded in porting the evolvable system to the hierarchy node and achieving the multi-objective evolution by enabling power awareness. The new platform meets the low power needs at the cost of longer execution time. As for future work, we are currently working on 2 lines. Firstly, implementing confluent hardware evolution so that several FPGAs carry out different evolutionary processes in a cooperative way. And secondly, we are approaching brain-computer interfaces as a generalization of the capabilities of evolvable hardware. Other results of this work include the elaboration of the hierarchy reconfiguration guide, which is currently being used by students to prepare for their final degree project. And this is all. Thanks for your attention. If you have any question, I will be willing to answer it.
Thank you very much, Blanca. Is there any question, please, José Antonio?
Yeah, very nice piece of work. I'm curious about the power that you save when you say lower power at the cost of longer terms. Do you have a quantification of those longer terms according to the power that you save, or elaborate that a little bit more? Thank you.
From the point of view of the porting of the system, the previous platform, I can say that it consumes like 10 times more. And looking from the point of view of how much we are saving by applying this multi-objective evolution, because I have not talked about figures, in fact, but almost among feasible solutions, the reduction can be around 5 or 10%. So it's not that much, but we have to take into account that in an FPGA, the power consumption is due to the interconnection mostly and to clock tree logic occupation. So in this work, the filter is always occupying the same area in the FPGA, and the interface is always the same, so the reduction cannot go to such an extent. But in the future, we plan to apply this evolution to scalable hardware, so the reduction can go much further.
Any other question? Yeah, please.
So the energy cost. So you added some circuits actually to measure the consumption, and also you have the sort of like energy cost of reconfiguration while operation. Yeah?
Mm-hmm.
So is this kind of also taken into account with the total efficiency and also the objectives?
Yes, regarding the circuitry to measure the consumption, the people of the same research group who developed this hierarchy node took into account that, and all the circuitry is low power, so the ADC is low power. And regarding reconfiguration, here the optimization is not applied to the evolutionary process, but only to the filtering process. So we don't take into account that reconfiguring we waste a lot. That in fact is true. Reconfiguration is one of the most power-consuming tasks. However, we only optimize here the filtering states, because it's the one that is going to exist in the node when it is in normal operation mode, filtering images.
Thank you, Blanca, for your presentation once again. We are going to continue with our speakers. Right now we are right on the half of this session. And